We are going to learn sequence and progression. A sequence of progression is an ordered list of numbers that follow a particular pattern or rule. 1, 2, 3, 4, 5, dot, dot, dot is a sequence of numbers. Starting from 1, we can generate the next number in the sequence by adding 1 to the previous number. So we say this is a sequence. To refer to this sequence, we can say within brackets x sub I, where I is in natural number, is equal to within brackets 1, 2, 3, 4, 5, dot, dot, dot. Important. Many books define natural numbers as the set of numbers starting from 1, and others define it as a set containing 0, 1, 2, 3, 4, dot, dot. Now, we are going to choose the first definition. We use a variable, say x, with a numbered subscript, say I, to refer to a particular element of this sequence. The subscript is called the index, and it belongs to the set of natural numbers. The rule can be written as, in this case, x sub 1 is equal to 1, x sub I plus 1 is equal to x sub I plus 1, or very simply as x sub I is equal to I, where I is in the set of natural numbers. So it's basically we are listing the natural numbers, and we are using natural numbers to refer to the elements in this list of ordered numbers. Okay, now this is another one, x sub n, where n is in the set of natural numbers, is equal to 2n, where n is in the set of natural numbers. This is the list of even numbers, or more specifically, positive even numbers. Of course, here we are excluding 0. X sub n is equal to 2n minus 1, where n is in the set of natural numbers. This gives us the sequence of odd numbers. There is a very special sequence called Fibonacci numbers. 1, 1, 2, 3, 5, dot, dot, dot. The rule is written as x sub I is equal to x sub I minus 2 plus x sub I minus 1, where x1 is equal to 1, x2 equal to 1, and I is greater than or equal to 3. So basically what this rule means, that starting with 1, 1, we keep adding the numbers to get the next numbers. So we add the previous to previous number and the previous number to get the number. So 1 plus 1, 2, 2 plus 1, 3, 3 plus 2, 5, and so on. Now let's look at a geometric example. Okay, starting with a triangle, we need to keep adding more triangles without duplicating line segments, side by side by side. So how would that look like? We have a triangle. It has 3 sides. We want to add one more triangle to it. We just need 2 more line segments. For the next triangle, again 2 more line segments. So our sequence or progression is 3 plus 2, 5, plus 2, 7, plus 2, 9, and so on. In tabular form, if you want to see, this is how it would look like. Triangles, 1 triangle, 3 segments, 2 triangles, 5, 3 triangles, 7, 4 triangles, 9. This progression may stop at this point or keep going indefinitely. If it goes indefinitely, we write those dot dots to signify that there are more numbers in the sequence. Now, similarly, with a square, we need to keep adding more squares without duplicating line segments. So here the sequence of progression is 4, 7, 10, 13. So we start with a square which has 4 line segments. To this, we add how many more? We need to add 3 more line segments to get the second square. Then 3 more for the third square, and so on. So again, in tabular form, we have 1 square 4, 2 squares 7, 3 squares 10, 4 squares 13 line segments. Again, this progression may stop at this point or keep going indefinitely. If it goes indefinitely, we write 4, 7, 10, 13, dot, dot. Now, we can have any number of sequences provided we can come up with a rule to satisfy. So, in general, it's written like this: A1, A2, dot, 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 generated by a rule which says that the nth term is equal to rule with the domain of n specified. So what do I mean by that? Let's say we have this sequence of numbers. I have 1, minus 1, 1, minus 1, 1, minus 1. So here the numbers are 1, but the signs are alternating. So we start off with a positive 1, then negative, positive, negative, positive, negative, and so on. Now the rule would be what? X sub n is equal to minus 1 to the power of n plus 1, where n is in the set of natural numbers. Now, whenever you look at such a rule, one thing that you should make sure is that the first term is satisfied by this rule. So, minus 1 to the power of, for the first term, what is n? N is 1. So, we have 1 plus 1. So, minus 1 to the power of 2, which is 1. So, that is satisfied. And then just take a few other and you can confirm the rule. Again, we have 12, 22, 32, 42, dot, 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 dot. This is generated by the rule x sub I is equal to 12 plus 10 times I minus 1. Now, why I minus 1? Because first number is 12. That is this. But then this should become 0 for it to be 12. So, this will become 0 only when I is 1. If it is 1, 1 minus 1 is 0, 10 is 0, 0, so 12 is repeating. So you have to be very careful with this I business. Okay, again, 13, 23, 33, pretty straightforward, very similar to that, is generated by x sub k is equal to 13 plus 10 times k minus 1. Why k minus 1? We have already seen. But here I wanted to explicitly show that the subscript identifier need not be I only. It can be any letter. It can be I, it can be K, it can be any other letter. Now, let's look at the next one. 1, x, x square, x cube, and so on. This can be also written as x to the power of 0, x to the power of 1, x square, x cube, and so on. Or as ai is equal to x to the power of I minus 1. For the first term, I is 1. So 1 minus 1 is 0. So we get the first term. For the second term, I is 2, 2 minus 1 is 1. So x to the power of 1. And so on. What about this? 1, 2, 4, 8, 16. Again, 1 can be written as 2 to the power of 0. 2 to the power of 1, 2 to the power of 2, 2 cube, 2 to the power of 4. Now, I have basically used this sequence itself, but I have specified that x equal to 2. So, where x equal to 2 in the previous sequence. Now, what about this? We have 1, 1 by 2, 1 by 4, 1 by 8, 1 by 16, dot, dot, dot. This is also a sequence. And general term is x sub I is equal to 1 by 2 to the power of I minus 1. where I is in the set of natural numbers. So the first term becomes 1 by 2 to the power of 1 minus 1, which is 0. So anything to the power of 0 is 1. When I is 2, this becomes 2 minus 1, 1. So that is 1 by 2. 3 minus 1, 2. So 1 by 4, and so on. Okay. Now this is again a special sequence similar to Fibonacci. This is called the Lucas sequence, where the sequence starts with x1 equal to 2 and x2 equal to 1. In the Fibonacci, we had x1 is equal to 1, x2 equal to 1. But the rule remains the same. Xn is equal to x sub n minus 2 plus x sub n minus 1, where n is greater than or equal to 3 and is in the set of natural numbers. Now, each of the numbers in the above sequences is called a term. So, in the sequence a sub n is equal to 2 plus 3 times n minus 1, where n is in the set of natural numbers, a1 is equal to 2 is the first term, a2 is equal to 5 is the second term. So the general term is a sub n is equal to 2 plus 3 times n minus 1. Now, there is a common difference between any two adjacent numbers. So that common difference would be the difference between any two adjacent numbers. So that we write it as d is equal to a sub n plus 1 minus a sub n. And this common difference can be positive or negative. Now, in this particular case, we have the sequence as 2, 5, 8, 11, dot, dot, dot. So you can see 5 minus 2 is 3, 8 minus 5 is 3, 11 minus 8 is 3, and so on. Okay, now let's look at this sequence. In the sequence 1, 2, 4, 8, 16, dot, 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 dot. If we take the common difference approach, what happens? Then we get 2 minus 1, 1, 4 minus 2, 2, 8 minus 4, 4, 16 minus 8, 8. So there is no common difference. The differences are 1, 2, 4, 8. So it doesn't satisfy this particular property. There is a common difference between any two adjacent numbers. So in this case, let's do one thing. Since the differences are not the same, so instead of subtracting, let's look at division. That is a sub n divided by a sub n minus 1. That means we take a number in the list and divide it by the previous number. So here what's happening? 2 divided 1 by 1, 4 divided by 2, 8 divided by 4, 16 divided by 8. They all give the same common ratio of 2. So here the ratios are the same, and this is called the common ratio. So we have common difference in some sequences, and in some sequences we have common ratios. The common ratio can be an integer or a fraction. So this brings us to a very important categorization of a sequence. A sequence is based on a pattern. If the pattern is based on addition subtraction with a common difference, it is called arithmetic progression. If the pattern is based on multiplication division with a common ratio, it is called geometric progression. That was, you can say, the introduction to sequences and progressions. If you found this session useful, don't forget to like, share, and subscribe. Questions, suggestions, and comments are always welcome. Thanks for watching. See you in the next session. That's it for now. Bye.